Alrighty, howdy folks. Chapter 14, Section 5, the chain rule. That's going to be the subject of today. Chain rule. I don't know, some people probably have nightmares about chain rule from Cal 1. But what I tell you, it's very, very easy. I mean, it's not really that complicated, but incredibly effective and also needed. You really need to understand chain rule because in so many places when you have to take a derivative, chain rule comes into play, right? And so let me start by helping you recall how the chain rule worked in 2D case, R2 case. R2. Did I talk about R2 before? It's just basically it's saying there are two axes. Say we can call them x and y axes, and x is a real number set, R, and y is also a real number set. So we have two real number sets on which our function is defined, right? So that's the idea. Okay, R2, y equals f of x equals g of t. What? Y is a function of x, and x itself is a function of t. So the question then becomes, maybe I'll put it this way, sorry. If y is a function of x, what is dy dx? Is that a fair question to ask? Yeah, of course, man. Dy dx. Yeah, that's the f prime of x, that stuff. But then when we got to parametric equations, this is what we saw. Y is a function of x, but no, you don't need to get to parametric. I take that back. If y is a function of x and x in turn is a function of t, now would you agree that means y itself is a function of t? What? Oh man. Y is a function of x. X is a function of t. So y is a function of t. Example, y is equal to x squared. Would you say that's a function of x? Yep, y equals x squared. Well, x equals t cube. Then y is x square, x is t cube, so y is equal to t cube the quantity square, which is t to the 6. So y is in fact a function of t, right? So the question then becomes, hey, if I want to find dy dt, what do I do? Dy dx is fairly straightforward, f prime of x, but I want dy dt because y is actually a function of t. Not in a straightforward way, but slightly indirectly. Well, chain rule says, don't worry about it, dy dt is nothing but dy dx times dx dt, right? It's like dx dx cancel each other out. If you want to think of it that way, that's perfectly fine. So dy dx times dx dt, that's the chain rule. And the multivariable version works more or less the same, but with a couple of differences. We don't have just one case, but we have two different cases in this one. As before, z is a function of x and y. X itself could be a function of t, and y itself is a function of t. So what this would give you is, do you remember back in the other previous chapter, if z is a function of x, y, x is a function of t, y is a function of t, then z is going to be a space curve. That's the thing. Z is going to be a space curve. And now let's say we want a derivative concept. Couple things. Can I say, when I have z as a function of x and y, can I say dz dx, the derivative of z with respect to x? Well, not quite. That wouldn't be quite right because z is a function of both x and y. In calculus 3, we learned that, oh, you better say partial z with respect to x, right? Not a regular dz dx, but partial z with respect to x. Similarly, partial z with respect to y. Okay, if that is the case, and it turns out that both x and y are functions of t, is it true that z is a function of t? You see my question? If z is a function of x and y are in turn functions of t, would that make z a function of t? Yes, it would. You want a simple example? Okay, z equals x times y. Is that a function of xy? When I say z equals xy? Yep. X in turn is t square, y equals t cube. So z is going to be t square times t cube, right? Which is t to the 5. So z is a function of just t. Cool. The reason I'm talking about that is, now can I talk about the derivative of z with respect to t? What kind of a derivative would that be? Is that an ordinary derivative or a partial derivative? Well, z is purely a function of t. The moment we use the x and y, z becomes just a function of the variable t. So we can use the regular derivative dz dt. We can say that. Okay. And it turns out it's fairly straightforward. dz dt is partial f with respect to x times dx dt. Sort of think of it as partial x and dx cancelling each other out, because they both represent what's the word? Differential. A differential dx, and in this case partial x sort of represents the differential dx too. So dx and dx, so we have partial f with respect to t. However, because f is a function of both x and y, we have to look at the contribution of the y component. So we have plus partial f with respect to y times dy dt. Because z equals f. Well, we can just simply, instead of f, we can say z. Partial z with respect to x times dx dt plus partial z with respect to y times dy dt. Wait. Does this make sense? Could you have a combination of a partial derivative and a regular derivative? Does it make sense to say partial z with respect to x? Partial. Yeah, that's because z is, like I said, is a function of both x and y, so we have to say partial z with respect to x. Okay, then should we say partial x with respect to t? Nope. Because x is purely a function of t. So we use the regular derivative dx dt. Right? So this is perfectly all right. Similarly, partial z with respect to y and regular derivative dy dt. That's it. There is no complication to it. And then there is a second case. And the second case is where z is a function of xy, just as before. But x is a function of two variables s and t. Similarly, y is a function of s and t. Cool? So in this case, we are interested in the derivative of z. Well, let's first start with, as before, can we talk about derivative of z with respect to x? Yeah, that would be a partial z with respect to x. With respect to y, yep, that's also going to be partial z with respect to y. But then, can we talk about derivative of z with respect to this s? Yes, we can. Okay. Is that an ordinary derivative dz ds, or is it a partial derivative partial z with respect to s? Well, if we use x as a function of s and t and y as a function of s and t, it turns out z in turn would be a function of s and t. And since z is a function of two variables s and t, it is imperative that we say partial z with respect to s. Similarly, partial z with respect to t. So those are the things that we are interested in case 2 when it comes to chain rule. So let's look at that. Partial z with respect to s. Well, that's simply partial z with respect to x times partial x with respect to s plus partial z with respect to y times partial y with respect to s. Partial z with respect to x, you should have no hesitation in saying that, right? Because z happens to be a function of x and y. But what's up with this partial x with respect to s? Yeah, that's also obvious because x happens to be a function of two variables, s and t. So we use partial x with respect to s. That's all there is to it. Okay. And similarly, partial z with respect to t is this. Now you might be wondering, what? Is it really that important? Oh my goodness, really important, this stuff. Like all your engineering classes, you will bump into this kind of partial differentiation that uses chain rule quite a bit. And in fact, my very last example, I will show you how to take what is called a Laplacian equation or diffusion equation in x and y and convert it to polar coordinates. Okay, and there you will use this partial, use the chain rule big time. And I'll also talk about why you need to know that. Okay, all right. Are we cool? Let's move on. Some simple problems. Use the chain rule to find dz dt. Given z is this and x is e to the pi t, y is e to the negative pi t. Right? Z is a function of x and y. X and y are in turn functions of just t. So z is a function of t, so it makes perfect sense to say dz dt. You remember what dz dt is? Dz dt is partial z with respect to x times dx dt plus partial z with respect to y times dy dt. I could have shown you that, hey, recall that we are what it is, but on purpose, this is what, if I were to be the student, I would be doing. I would look at this and say, wait a minute, and I would, if I were you, I would pause the video and go, at this time, what is dz dt? What's that formula? That was just in the previous slide. So you try to memorize some of those things with an understanding as and when they pop up. Okay? And when you do that, you will have a much better chance of memorizing, and you keep testing yourself. Wait a minute, I just looked at it a minute ago, less than a minute ago. Can I recall what it is? Keep doing that. Helps you a lot. Okay? All right, so what is that? dz dt is, like I said, partial z with respect to x times dx dt. So would you agree it's all pretty straightforward? You need partial z with respect to x. Can you figure that out? Yep, you know z as a function of x and y. We know exactly how to find partial z with respect to x. Similarly, dx dt, x is e to the pi t. We know exactly how to find dx dt, and similarly other ones. I think I used what? Yep, the quotient rule, x plus 2y times 1 minus the numerator times the derivative of the denominator with respect to x, so y would be held constant, and the denominator square over the denominator square, which is that good old lodi ha minus haddy low over low low, right? You do that and simplify it a little, and you get this. That's partial z with respect to x. Cool. Partial z with respect to y. Similar thing. Quotient rule. And that turns out to be negative 3x over the quantity x plus 2y square. What else? Oh, we need dx dt. X equals e to the pi t, so dx dt is pi e to the pi t. How'd you get that, man? Simple, right? E to the anything is e to that something times the derivative of the pi t itself, which is pi with respect to t. Derivative of pi t is just pi. So pi e to the pi t. Y equals e to the negative pi t, negative pi e to the negative pi t, right? Cool. Just a matter of plug and chug. I'm sorry. Did I insult your intelligence? Come on, man. We are in Cal 3. We know how to do this stuff. I suppose you could factor out some things like a 3 pi over the quantity expression and write it as e to the y e to the pi t plus x e to the negative pi t. Okay. Simple. Let's move on. Use the chain rule dz dt. Okay. Similar concept, except the functions are just a tad more harder to differentiate. Let's go with it. Apply case 1. That is that formula. Partial z with respect. What? Ah, see, this is what happens when you copy. When I was making this slide, I copied the previous slide and changed things that I needed to change. Samuel. Z is not equal to this. Backslash square root of 1 plus xy. Right? Okay. Oh man. I need to move all these guys to the right. Okay. Typing up all these things is such a pain, I'm telling you. And have to create separate text boxes, and so that each one will pop up when I want it to. Okie dokie. Sorry about the delay and my goof up. Z equals square root of 1 plus xy. So partial z with respect to x. I somehow ask students to memorize the derivative of square root of x. If I say y equals square root of x, what's dy dx? 1 over 2 times square root of x. 1 over the quantity, 2 times square root of x. That's a good one to memorize. But look at this. So this, to me, is like, as soon as I say this, partial z with respect to x. Okay, 1 over 2 times square root of 1 plus xy. Just blindly write down that. And then times the derivative of the inside stuff, inside the radical, 1 plus xy itself. And that's how we get the derivative. 1 is 0, xy with respect to x, the derivative would be just y. Cool? Yeah, we can write like that. Similarly, if z is that, what is partial z with respect to y? 1 over 2 square root of 1 plus xy to begin with, times the derivative of 1 plus xy with respect to y, partial, is x. Cool. Now we need dx dt. Ooh, x equals tangent t, dx dt. Remember, secant square t. Y is arctangent of t. 1 over 1 plus t square. That's it. So that's the only complication with this one. Cool. That's it, folks. About at least this problem. I hope it all made sense to you. All made sense to you, It all made sense to you. I don't quite do it the right natural way, right? Alrighty. What's this now? Ooh. The Case 2 situation. Use a chain rule to find partial z with respect to s and partial z with respect to t. Given z is a function of x and y, but x is a function of s and t, y is also a function of s and t. So, let me see if I can recall. Partial z with respect to s is partial z with respect to x times partial x with respect to s plus partial z with respect to y times partial y with respect to s. Yeah. Oh man, there was a course called Vibrations of Continuous Media that I took as a grad student. And that one, and also Continuum Mechanics was another course. In all those courses, we did this stuff day in and day out. As an engineer, I didn't know this way of, formally presenting it. I just intuitively, I saw that and the professor wrote something and I figured out that's what he's doing. I wish I had known more formally, like you guys are learning this stuff. I'm sure in India they must have taught this, and I was a pathetic student in college and never bothered to listen. That's bad. I sincerely hope you're not like me. Cool. Z equals this. I did copy the right one. Partial z with respect to x. We gotta do a product rule for this one, right? So first function square root of x times e to the second function, derivative of second function is e to the xy times chain rule y plus second function e to the xy times the derivative of square root of x is 1 over 2 square root of x. And we can simplify and factor out a e to the xy and write like that. And similarly, partial z with respect to y. There is no need for a product rule on this one. So we say square root of x, e to the xy times x, and is that true? A square root of x is just a sort of a constant. E to the xy, the derivative partially with respect to y would be e to the xy itself times the derivative of xy, which is x. So that's x square root of x e to the xy. Okay, simple ones. Partial x with respect to t is s. With respect to partial x with respect to s is t. Partial x with respect to t is s, right? Similarly, y equals s square minus t square. Partial y with respect to s is 2s. Partial y with respect to t is negative 2t. Yep. Plug and chug. That's all there is to it. Cool. I wonder. Right now we have partial z with respect to s in terms of x and x, y, s, and t. All four variables are showing up, right? Well, it is possible to replace the x with a 1 plus st and a y with an s square minus t square. That way you won't have all the four variables. But I'm not going to do that. And I think if I were to be teaching like a regular class, you leaving this answered this way is perfectly fine. Full credit. Okay. Let's see. A similar thing, folks. All right. Moving along. Yeah, this is the one. This, I think, goes on for 3 slides. Lots and lots of algebra and putting things together. So I don't know how much in detail I'm going to go through this, but I'm doing this for your benefit. Here is the idea. usually there is something called a diffusion equation. For example, if you take a bucket of water, no, don't take a bucket. Take a what's that? These guys in biology, they have petri dish. Yep. Yeah. Petri dish. Take a petri dish and pour some water. Okay, just shallow amount, and then imagine dropping a dye, a blue ink or something like that, right in the middle of that one. What will you notice? You will notice that the dye spreads, right? That process of the dye spreading into the entire volume of that water is called diffusion. And it so happens that after some time, no, let me put it this way. Even though initially only the center of that petri dish had this dye and the surroundings were all pure, just pure water, with time, diffusion takes place and the entire water becomes colored. And everywhere there is a uniformity of that color. So when that happens, we say that the diffusion has reached a steady state, because now all of the water has the same concentration of the dye. Now, can you imagine, as engineers, both chemical engineers and civil engineers who would be studying environmental kinds of things, how important something of that kind would be for you? And similarly, we could talk about temperature diffusing. If you imagine a plate and you heat up the center of it, then that heat is going to spread and the whole plate is going to be heated, but the whole plate is going to be heated. Let me leave it there. So that is governed by this equation, second partial, if you're talking about temperature, T with respect to x plus second partial T with respect to y is equal to some function. In the case of diffusion of the concentration, the dye thing, maybe you call the concentration as uppercase C or phi. So if you will study it that way. But then, what if we are talking about something that has radial symmetry? What do I mean by radial symmetry? A circular pipe. Would you agree that a circular pipe has radial symmetry? It is symmetric no matter what angle you pick, it's the same radius. So that's said to have a radial symmetry. In analyzing those kinds of things, everything becomes so simple if you convert into polar coordinates. And that same diffusion equation in xy coordinates, when converted to polar coordinates, becomes this equation. Now, does it look like this one is much harder than the x and y thing? Yeah, it is. So what's the advantage? The advantage is what are called the boundary conditions would be much simpler when you express in polar coordinates for something that has radial symmetry. So you will learn all these things in detail when you take some of the engineering classes, and you will bump into this equation, and you will be expected to know how to convert partial derivatives in x and y to partial derivatives in r and theta. That's why I'm showing you this. The process itself is fairly straightforward, like we talked about. It's just a tedious, long thing. Watch this. Partial z, yeah. By the way, do you recall that x equals r cosine theta, y equals r sine theta is the way you You go from polar coordinates to Cartesian coordinates. X is r times cosine theta and so on. Yeah, cool. So when you do that, partial z with respect to x, partial z with respect to r, if we were to evaluate that, then that's partial z with respect to x times partial x with respect to r. Right? Notice what I'm finding. I'm finding partial z with respect to r. My eventual objective would be to find second partial z with respect to r and also second partial z with respect to theta. Okay, and so let's get on with this. So partial z with respect to x. Now, what about partial x with respect to r? I seem to be saying that's equal to cosine theta. Do you agree with that? Yeah, you should, because notice x is r cosine theta. So partial x with respect to r is just cosine theta. Theta is to be treated as a constant, so cosine theta is to be treated as a constant, and so partial x with respect to r is just cosine theta. Similarly for the partial y with respect to r. Cool? All right. Now, what is the second partial of z with respect to r? Please pay attention to this part. I think I may have mentioned this somewhere else. To me, when I look at partial z with respect to r, I want to think of it as partial with respect to r of the quantity z. Partial with respect to r of the quantity z. That is because I can then say, oh, you mean that is equal to partial with respect to x of the same quantity z times partial x with respect to r? Yep. Partial with respect to y of the quantity z? Okay. Now, you will see why I say it's a good way to look at it that way when you come to second derivative. When we have second partial z with respect to r, I want to look at it as partial with respect to r of the quantity partial z with respect to r. Okay. So what's the difference between partial this and this? Oh, the only difference is up here we had partial with respect to r. The quantity was just a z. However, here the quantity happens to be partial z with respect to r. In both cases, we are taking partial with respect to r. What changed is just the quantity. Over here it was z. Over here it is partial z with respect to r. Okay, so what happens? Well, that's precisely what happens. You change the quantity. The quantity was z here, so partial with respect to x of z. Here we have partial with respect to x of the quantity partial z with respect to r. And what about this partial x with respect to r? Yes, you just leave it alone. Times partial x with respect to r. That's the advantage of looking at partial z with respect to r as partial with respect to r of the quantity z. Cool? All right. And then the rest of it is plug and chug. Partial with respect to x. We know partial z with respect to r from the previous step. I'm looking at that. I'm plugging that here. Times partial. So it's just a patience game. Okay, now let's look at this. What is partial with respect to x of the quantity? Partial z with respect to x times cosine theta. Well, would you agree? That is second partial of z with respect to x times cosine theta. Right. And so again, this is second partial z with respect to x and y times sine theta. Yeah, because we are dealing with partial with respect to x and partial x with respect to r, we already saw that was cosine theta. I just plugged that in. And second partial z with respect to y and x times cosine theta, and so on. All right, so that ends up being, we have a cosine theta times cosine theta, and we end up getting this. All right, you can pause the video and look at it, or maybe take a piece of paper and write it and check for yourselves. All right, next, note that x equals r cosine theta, y is r sine theta. So partial x with respect to theta is negative r sine theta. R times the derivative of cosine theta is negative sine theta. So negative r sine theta, and partial y with respect to theta is r cosine theta. So when we are looking at partial z with respect to theta, earlier we did partial z with respect to r. Now let's look at partial z with respect to theta. And that turns out to be this. And negative r sine theta is nothing but negative y. And r cosine theta turns out to be x. So second partial z with respect to theta, like again, the quantity has changed from z over there to partial z with respect to theta, and I use that concept. And plug and chug, a whole bunch of these things, and that ends up being this. A little more involved. And if we put together all of this, we need to show that. And we figured partial z with respect to r and second partial z with respect to r, second partial z with respect to theta. So those are the things that we had so far, right? We found every one of these quantities that on the right hand side. So let's plug those things. So the right hand side, RHS is right hand side, is second partial z with respect to r, blah blah, and I'm going to plug things. And when I do, my claim is that y square over r square is sine square theta. That's because y equals r sine theta and x equals r cosine theta. And also y over r square would be r sine theta over r square is 1 over r sine theta. X over r square is 1 over r cosine theta. Why am I looking at it? There are going to be some substitutions that I would be making. Okay, and so, whoa, when we do that, that whole thing just becomes second partial z with respect to x. Abracadabra, alakazoo. Really? Yeah, really. Okay, let's see. Second partial z with respect to x, cosine square theta from here. Now here I have y square over r square. Is that sine square theta? So do I have second partial z with respect to x sine square theta? Earlier, do I have second partial z with respect to x cosine square theta? Now, am I adding these two quantities? So can I factor out a second partial z with respect to x so that I get cosine square theta plus sine square theta? That's equal to 1. Are these the only two terms with a second partial z with respect to x? You bet. So that's why you get this. Now, second partial z with respect to y sine square theta and second partial z with respect to y x square over r square is cosine square theta. X square over r square is cosine square theta. So again, we get second partial z with respect to y. But what about all the other terms, man? Yeah, let's look at them, man. 2 times second partial z with respect to y sine theta cosine theta. And here we have, if we look at xy over r square, then that is 1 over r square sine theta cosine theta. What is that? What did I say? Geez. 2 xy over r square. Let me see what happens to xy over r square. Or should I just look at x times y? No. Okay. Y equals r sine theta. Why am I making such a big deal about this? Simple. Sorry about this. X is r cosine theta. Y is r sine theta. Right? Isn't this r square cosine theta sine theta? Am I not dividing by r square? R square over r square. So just give me cosine theta, r square sine theta. So I have a sine theta cosine theta minus 2 second partial z with respect to xy. That and this cancel out. That's all I'm trying to say. So we accounted for this guy. We accounted for this, this, and this. So what we are left with are these 4 terms. 1, 2, 3, 4. Okay. Y over r square is 1 over r sine theta. Okay. So y over r square is 1 over r sine theta, and this is a partial z with respect to y times 1 over r sine theta. There's a plus 1 over r partial z with respect to y sine theta. They add up to 0. Similarly, x over r square is 1 over r cosine theta. And so 1 over r cosine theta partial z with respect to x with a negative, and 1 over r partial z with respect to x cosine theta with a positive, they add up to 0. Cool. And so the only things that survive are this, and that is in fact left hand side. Let me put your minds at ease. I am not going to ask you in a test to do this derivation. It is something that you definitely want to print out and keep it with you, because it's entirely possible that one of your engineering classes you'll be given a homework problem asking you to do precisely this. Okay? Did I just encourage you to cheat? Oh, I'm such a bad person. Ladies and gentlemen, that concludes this particular section. That's all.